All right, let's get started. Obviously, we're winding down here, right? These semesters have a way of both like flying by and going by really, really slowly, all at the same time. We're coming to the finish line here. All right, I know everybody had a wonderful time not thinking about chemistry last week, but you got to click back in. We got a few more weeks to go here, okay? My goal for today is to kind of pick one compound, and we're going to try to pull as much stuff from as many different chapters as we can to help talk about this one little compound here, all right? Basically, the idea is to kind of rewind and give a sense of all the stuff that we've covered so you can be like, oh yeah, I totally remember all this, great, or oh crap, I really need to go and study that chapter again, okay? So we're going to talk a whole bunch today about the compound NH3, which we have a common name for ammonia. All right, this compound here, actually, if I'm being really good with my Lewis structure and showing all my bonds and my lone pairs, we have a nitrogen that's bonded to 3 hydrogens, and it has this lone pair on here. This compound is really important. It's quite a simple compound, right? Just nitrogen and hydrogen. It also sort of plays an outsized role in organic chemistry. There are a lot of organic molecules that contain this as what we would call a functional group, and that controls the chemistry of that particular molecule. Okay? In particular, ammonia is a weak base. All right, so if ammonia is a weak base, let's remember we talked a lot about acids and bases this semester. You should be able to give me the formula for its conjugate acid. Okay, so if this is a base, remember a base accepts a proton, a hydrogen ion. So my formula here, I'm going to increase in my number of hydrogens. I go from 3 to 4. All right, but it's also accepting that positively charged hydrogen, so my charge also goes up by 1. All right, and we don't talk too much about structure, but just because I think it's interesting, if we drew the structure of this ammonium ion here, we would see that what happens, and this is typical of acids and bases. Acids and bases are something you study in like a lot of chemistry classes. You'll do an additional deep dive if you go on to organic chemistry. But this lone pair is always really important in a base. This is what becomes this new nitrogen-hydrogen bond. All right, that pair of electrons that used to be that lone pair becomes a covalent bond when you go from being a base to its conjugate acid. All right, importantly though, we worked on these formulas here. So the NH4 plus should be what we can do based on what we studied this semester. Okay, and so this is its conjugate acid. And so just to remind ourselves of what that means to be an acid is a proton donor. Right, so this donates H+. And if ammonia is a weak base, what can we say about its conjugate acid? Is it strong, weak, or neutral? Weak. Awesome. Okay. All right, cool. So then let's say that we're going to take 33.5 grams of ammonia, and we're going to dissolve in 355 milliliters of water. What is the concentration in molarity? All right, so let's think real quick. What symbol do we use for molarity? The big M. And what does that big M stand for? Moles over liters. And in particular, if we're being really good, it would be moles of solute divided by liters of solution. So actually, I guess I have to say 55 mils of dissolved to create, crap, hold on. Let me be really good about my wording here. Dissolved in H2O to create 355 mils of solution. So that's my total volume here, is that 355. Okay, so what is the concentration in molarity? So let me take this so we can see these numbers. And since we're asking for moles over liters, we're going to need to rewind back to our 1A knowledge and use our periodic table here to calculate the number of moles of ammonia we have. Our molar mass of our ammonia is the molar mass of nitrogen plus 3 times the molar mass of hydrogen. Okay, so I'm going to take that 14.00674 and then add 3 hydrogens. Each has a mass of 1.00794. I get 17.03056 grams per mole. All right, so let's just take that back to our other page here. This is our molar mass of ammonia. All right, so how am I going to use my mass and my molar mass to convert from grams to mole? All right, remember, it's all about the units, all about setting this up in such a way that your units cancel out. I'm trying to cancel out grams, so I'm going to divide by that 17.03056. That's grams, and that will put me in moles of ammonia. So 1.96705, write down a bunch of digits. I'm going to mark my sig fig with a bar here. And again, my units will be moles of ammonia. So now I need to take that and divide it by the liters of solution. Here I'm given 355 milliliters. So I'm going to have to use the fact that there are 1,000 milliliters in 1 liter, or 0.355 liters. All right, so then in order to get my concentration, and remember we use this bracket notation for concentration and molarity, I'm going to take my moles of ammonia, okay, I'm going to divide it by my liters of solution. And I get 5.5409. Big M, right? Moles per liter. And if I'm being good about my sig figs, how many sig figs should I round my concentration to? I got 3 in my moles here, right? That came from my mass. I have 3 in my volume here. So I'm going to round this off to 3 sig figs. So my concentration of ammonia in this solution is 5.54 molar. All right, cool. So let's figure out what the pH of this solution is. Going back to our acids and bases chapter here. Okay, in order to do that, we need a Kb reaction. So everybody take a second. Ammonia, solution of pneumonia. Ammonia rather, not pneumonia. Okay, how are you going to finish this balanced chemical equation for our Kb expression? This looks ugly. Okay, so we're talking about a Ka reaction or a Kb reaction. We always have the same reactant here. In this case, it's Kb, so this is a base. What is it that's playing the role of the acid in this reaction? Water, awesome. And my base is going to accept a proton, so then I have to give my formula for my conjugate acid that we've done before. That was that ammonium ion. And then what is my conjugate base? It's got a very fancy name. This is the hydroxide ion. Okay, and Kb, that K is an equilibrium constant. So now, given our chemical equation here, take a second and give me my equilibrium expression for this reaction. All right, equilibrium expressions. What do we remember? What over what? Products over reactants. If you remember nothing from this course, I really hope you remember products over reactants. All right, so we have our ammonium ion and our hydroxide ion, concentration of each, right? The brackets are concentration. And then on the bottom, I'm just going to have ammonia here. Why do I get to omit water? Because of the liquid. Right? Aqueous or gaseous will appear in your equilibrium expression. Solids or liquids do not. And because this is a particular equilibrium constant here, again, what we call Kb, we have these values. We can go and look it up for these bases. All right, so I'm going to go to my handy-dandy constants page where I have Kas at the top and Kbs are listed at the bottom. I'm going to find it for ammonia, alphabetically the first, so it makes my life easy. All right, 1.76 times 10 to the negative 5. All right, so again, our ultimate goal here is to figure out what the pH is of our solution of ammonia, right? The solution that we just calculated has a concentration of 5.54 molar. We have our balanced chemical equation, that's step 1. We have our equilibrium expression, that's step 2. What's step 3? Ice table, right? Whenever we're trying to fill in our equilibrium expression, 9 times out of 10, the strategy is building that ice table. All right, so we have the concentration of all those components from our Kb expression. And we have on these columns the ice part. And so let's just remind ourselves what this stands for, because it's been a minute. This would be the initial amount. In this case, we're talking concentration, so the initial concentration. C is the change that we see as this approaches equilibrium. And then finally, E is our equilibrium value. All right, once this system reaches equilibrium, what is the amount of each of these components? And if I'm starting out with my solution of my 5.54 molar ammonia, that's what I'm going to put in my initial box here. And to start out with, I have no product yet. Now, I don't know what that change box is. I don't know how much of this ammonia is going to be consumed in the reaction. That's what we're trying to figure out, all right? So for these change boxes, we're just going to use a variable here. We're going to use x. All right, but see if you can remember what the sign of x should be in each of these boxes. All right, what's going to be the sign of x in the ammonia box? This would be minus, because our reactants get consumed as this reaction goes on, and our products get produced, so their concentrations go up. Just to sort of note, if this was a more complicated balanced chemical equation, I would have to include those coefficients in my change box, but this is all 1-to-1. And then finally, to get the equilibrium box, I'm going to sum everything up, right? So the I plus the C, so 5.54 minus x, 0 plus x is x, and 0 plus x is x. All right, and then out of all these 3 equilibrium boxes, I'm talking about trying to find the pH. What am I really interested in here? What is it that's going to help me find my pH? Exactly, right? The hydroxide ion concentration at equilibrium. That's what I'm trying to find here. Okay, cool. So now let's just take these E boxes and plug them back in. Right, I have my concentration of ammonia at equilibrium. I'll plug that in there. I have my concentration of ammonium at equilibrium. Plug that in there. Concentration of hydroxide. Plug that in there. So I get my Kb is equal to x times x, or x squared, over 5.54 minus x. And again, we looked up what that Kb value should be, 1.76 times 10 to the negative 5. All right, so again, I'm going to stop here and I'm going to give you a few minutes. Again, I want to know what is the pH of this solution. Everybody take a second and see if you can't finish off this problem, given where we are. All right, so again, pH, what I'm really interested in is this concentration of hydroxide, so I gotta solve for X. That's step one. All right, my Kb expression here, if I'm an algebra master, I can just solve for X using the quadratic formula, but we could also make our lives a little easier by noting that since this is a weak base, our value for X here, the amount of reaction that actually occurs is quite small. And so I can omit 5.54 minus X is basically just 5.54. All right, so I'm going to rearrange this expression here. I get X equals the square root of that Kb value, 1.76 times 10 to the negative 5, times that concentration of 5.54. And so I get a value of X of 0.00987. And again, X is my concentration of hydroxide. I'm looking for the pH, so I'm going to take the negative log of X, and that will give me pretty much 2 flat. 2.005. All right, so I'm done? No, because this isn't the pH, but the pOH, which checks out because this is a basic solution. So I should have a high number for my pH, a basic solution. So to get the pH, I got to do one more step. I got to use the fact that pH plus pOH equals that magic number 14. So I take 14 and subtract my pH, and I get 11.995. And again, this solution is basic, which again checks out because we added a base. And what it means to be basic is that the pH is greater than 7. Okay. Cool. So we got our pH of our solution. What was our constant? Oh yeah, 5.54. So we have this solution of ammonia. We know its concentration. We know what the pH of this solution is. We're going to titrate with 15.6 molar HCl. All right. We have a few different titration problems that we learned how to do. They're kind of on the longer end in terms of how much time they take to do, and we already did a pH problem with an ice table, so I'm going to skip to one of the shorter ones here. And what I could ask you, and this is actually almost more practicing your solution stoichiometry, is what is the volume of HCl required to reach the equivalence point? I guess I should note that we had 355 milliliters of our solution here. All right, so let's just take a second and think about this. Obviously, the key vocab word here is equivalence point. If you don't know what it means to be at the equivalence point, you're going to be in trouble for the rest of the problem, right? So what does it mean to be at the equivalence point in our titration? That means that the moles of acid are equal to the moles of base. All right, so step one, we got to figure out how much base we have. Moles of NH3. Once we have moles of NH3, that's just going to be equal to the amount of HCl. But then we need to use those moles of HCl and the concentration of HCl to calculate volume. All right, so how do we get moles of ammonia? Well, first of all, if you were clever, you could just go back up to the very beginning where we figured out how many moles of ammonia we had. All right, but importantly, I wanted to try to practice working with these solutions, working with this concentration and this volume here in order to get to your moles of ammonia. And the key here is how we turn this piece of information into something that we can actually use in our math that's going to help us cancel out our units. All right? So again, that big M is moles per liter. So the first thing I'm going to do is I'm going to take my 355 milliliters of solution, and I'm going to convert that to liters using the fact that there are 1,000 milliliters in 1 liter. All right? And then the key here, again, is now I'm going to take this piece of information, this 5.54 big M, and I'm going to turn it into something that I can use in my math, where I take my 1 units, my 5.54 moles of ammonia over 1 liter. All right, these two pieces of information that I've highlighted in orange are the same thing. This is how we see it in our problem, all nice and summarized with that big M for molarity. When we use it in our math and we can make sure that our units cancel out, we're going to stack moles over liters. Okay? And I could also take this thing and flip it upside down if I needed to, but here I know it's set up correctly because I got moles on the bottom. Oops. All right. So punch this into my calculator. I get my 1.9667. Be good about my sig figs here. All right, and again, we know it's set up correctly because if we look at our units, milliliters cancel out, liters cancel out, and I'm left with just moles. All right, moles of ammonia. All right, and again, to be at the equivalence point, that means that my moles of acid equal the moles of base. So that means I also have 1.9667 moles of HCl. All right, so in order to figure out what volume of HCl I need, I'm now going to have to use my concentration, that 5.56 big M. All right, if you haven't already, take a minute to see if you can't get me from moles to liters using that concentration. All right, so again, that 15.6 big M, I'm going to split it up into 15.6 moles over 1 liter. But what's the problem here if I just multiply these two together as is? None of my units are canceling out. I'm left with moles squared over liters. That's not a thing. Doesn't exist, right? So instead, I'm just going to take this exact same thing and flip it upside down so that the moles are on the bottom and the liters are on the top. Boom. Now it's set up correctly. My units will cancel out. And I'll be left with the volume of that solution that I need to reach my equivalence point. Okay, 0.126 liters, or maybe more conveniently represented as 126 milliliters. All right, but that's the volume that I would need to add of this 15.6 molar hydrochloric acid in order to reach my equivalence point in this titration. All right, and since I've added exactly as much hydrochloric acid as I had ammonia to begin with, at my equivalence point, I have a solution of just ammonia, just ammonium, NH4 plus, which we said was a weak acid. So we're not going to do the whole thing here, but if I wanted to figure out what this pH of this solution of weak acid was, I would need a Ka. How do I get it? All right. Well, first of all, we got this table of Kas. So this is a great place to start. But unfortunately, I don't see my ammonium ion there at all, right? I don't have a Ka specifically listed here. What I have is the Kb of its conjugate base, that ammonia that I started out with. And remember, we have this relationship, Ka times Kb equals that magic number we call Kw, 10 to the negative 14. So in order to get my Ka, I'm going to take that 10 to the negative 14 and divide by that Kb value. Okay, so then my acid dissociation constant, my Ka, would be 5.68 times 10 to the negative 10. And I could use that value to figure out what the pH of my solution is at my equivalence point. All right, but yes, we have this special relationship between Ka and Kb. If you can't find a particular compound on this table, but you can find its conjugate, you can always figure out what its dissociation constant is using this relationship. Okay. All right, so one way that we can prepare ammonia is just starting with nitrogen gas and hydrogen gas. Oops, also diatomic. In order to prepare some NH3, some ammonia. And ammonia in its pure form is a liquid. All right, so this chemical equation right now is worthless to me. What's the problem with it? It's not balanced. So everybody take a second to balance this chemical equation so we can use it. All right, cool. So now I have a balanced chemical equation. Let's make this a little more interesting. We're going to do this at a higher temperature so we can have a gaseous product here, I think. Let me not make any promises. Hold on. We got both. Because remember, as long as we can find both of these compounds on our nifty table here, excellent. Boom. Cool. All right, so now let's figure out the delta G naught of this reaction. And for that, we're going to need to go to that constants page and grab a bunch of values corresponding to each of these components here. Oh, whoops, wrong table. All right, so we had ammonia. Cool. I need my nitrogen. My hydrogen. Dang it. A, B, C, D, F, G, H. All right. Ignore this. Cool. All right, and if we looked at our constants page, we see that this first column here is the delta H naught values, then G, then S. So again, everybody take a second and calculate the delta G naught of this reaction. Remember, for equilibrium constants, we remember products over reactants. For these thermodynamic values, we remember products minus reactants multiplied by their stoichiometric coefficients. All right, so since we're talking about delta G, again, we're going to do products minus reactants. So 2 times that negative 16.4 minus the sum of my reactants, but they're both 0, right? So 3 times 0 plus 0 is just 0. Okay, so negative 16.4. All right, we get negative 32.8, and our units for delta G are kilojoules per mole. All right. Cool. So this tells us that this reaction is what? Spontaneous or non-spontaneous? Spontaneous. Negative delta G is good. This would be a spontaneous reaction, meaning that at standard state, it will indeed proceed towards the product side. All right. Now let's calculate our delta S naught. Our, what is the S? Entropy. But before we do that, let's take a look at this balanced chemical equation here and see if we can't figure out whether this reaction should be entropically favorable or unfavorable. Is this a reaction that creates more disorder or creates more order? So let's just take a vote here. Who thinks that this is an entropically favorable reaction? And what about unfavorable? Cool, so this is indeed an entropically unfavorable reaction. So why is that? We have a bunch of gases on either side, and gases are the most entropically favorable, okay? But the difference is I have 4 moles of gas on my reactant side, right? 4 little molecules floating around in space, and they're going to combine together to create only 2 molecules of ammonia. So I am indeed creating more order in this reaction. So we would expect, and let's see if our calculations are correct here, that this would be entropically unfavorable, which means what for the sign of delta S, positive or negative? This is a tricky one, all right? All the other thermodynamic variables, negative's good, right? Negative delta H is good. That's exothermic. Negative delta G is good. That's spontaneous. Entropy is the opposite. It's a positive entropy that means it's entropically favorable. That's good. So a negative entropy would be entropically unfavorable. Okay, and so given our table above, everybody take a second to calculate that delta S naught. All right, this one's a little bit more difficult of a calculation. We don't just have a bunch of zeros going on, so let's make sure that we got this down. All right, I'm going to use that stoichiometric coefficient of 2 of my product times the 192.8 minus, and I'm going to put in parentheses so I make sure that that minus sign is distributed to both of my products. My 191.6 plus 3, and again 3 because that's my stoichiometric coefficient, times the 130.7. Punch that all into my calculator, and I indeed get a negative delta S for entropically unfavorable. All right, and if we forget, we can always go back to our constants page just to check our units. Remember that both delta H and delta G are listed in kilojoules, but our entropy is listed in joules, and so we're going to have to account for that. Specifically, joules per mole Kelvin. All right, and just for the sake of time, I went ahead and calculated the delta H for this reaction as well. That was negative 91.8. And again, delta H's are in kilojoules as well. All right, so what will we say about the exchange of heat in this reaction? Is it endothermic or exothermic? Negative delta H is exothermic. Cool. All right, so what we did with all these calculations here, specifically and most importantly with delta G here, is we calculated the delta G naught of this reaction. So that's assuming that this reaction is at standard state, and one of our conditions of standard state is a very specific temperature, 298 Kelvin. This particular reaction is entropically unfavorable, but it is exothermic. So from the universe's standpoint, on the one hand, it's okay because it releases heat. But on the other hand, it's not too pumped about it because it creates order. All right? So we got this push-pull going on in the thermodynamics of this particular reaction. All right? If we look at the relationship between these two variables here, these two thermodynamic variables, our delta G is equal to delta H minus T delta S. And I want you to look at this equation here and our values that we got for delta H and delta S, and tell me what whether or not this reaction would be spontaneous or non-spontaneous at low temperatures versus high temperatures. Right? Spontaneous or non-spontaneous. All right, so remember, spontaneity is determined by the sign of delta G. A negative delta G is a spontaneous reaction. A positive delta G is non-spontaneous. All right, let's look at this equation here and imagine that we plug in a really small number for temperature. Let's say so small that it's 0, and it cancels out that term altogether. Would this reaction be spontaneous or non-spontaneous at that low temperature? Spontaneous because of my delta H sign, right? So from an enthalpy standpoint, this reaction is favorable. So it will be spontaneous at low temperatures. But now what's going to happen as I increase temperature? As this term right here gets bigger and bigger and bigger, and this is an entropically unfavorable reaction, all right? So this is just going to increase the value of delta G. Eventually, I'll get to some temperature where this reaction becomes non-spontaneous, right? So if it's entropically unfavorable, but enthalpically, whatever, exothermic, right, then it will be spontaneous at low temperatures, but at some point you're going to reach some temperature where that entropy term dominates, and this reaction will no longer proceed spontaneously, okay? So let's just pick a random super high temperature. Let's say, all right, cool, we're going to crank it up to 700 Kelvin. Is it spontaneous? Remember that if we want to figure out our delta G at any other temperature than at standard state, we have to use instead this equation here, where we're going to plug in our delta H naught and delta S naught. These values do change a little bit with temperature, but not much. All right, so we can use this equation here, given these two values that we calculated, to figure out whether our delta G is still positive or still negative, or whether we've clicked over into that non-spontaneous region. Okay, so everybody take a second and calculate the delta G for me at 700 Kelvin. All right, so I plugged in my value for delta H. I plugged in my temperature. And then I plugged in my value for delta S. But I was also really good and I put in my units here. And we can see what's the problem that I'm going to have here. What's my energy units of this term? The kilojoules. What's my energy units of this term? Just the joules, right? So this is kind of a pain in the butt way in which these thermodynamic variables are listed. They have different units associated with them. So I'm going to need to convert. I could actually do either and I would get the same answer, or I would get, the same idea, but nonetheless, I'm going to convert my kilojoules to joules by dividing by 1,000. There are 1,000 joules per kilojoule. So then in the end, my answer will be in kilojoules per mole, which is a typical way of representing free energy values. And indeed, I have a positive 46.87 kilojoules per mole. So now we have reached a high enough temperature where this reaction is no longer spontaneous. It is now non-spontaneous. All right, again, because of this push-pull between these two terms, between my enthalpy value and my entropy value, when I get to a high enough temperature, this term will dominate and this reaction is no longer favorable. All right. Cool. So one more thing that we're going to say about this reaction here, all right? I'm going to tell you what the reaction mechanism is. Okay, it turns out that this reaction is broken down into two elementary steps. Step 1, the nitrogen gas collides with just two hydrogens. To make N2H4 gas. And then finally that N2H4 gas collides with the second hydrogen to produce our two ammonias. Okay, so step 1, let's convince ourselves that this is a legit mechanism here by summing these two elementary steps up. All right, so I'm going to put all my reactants side together. I'm going to kind of do this the long way here. N2 gas plus 2H2 gas plus now my second step reactants. Okay, so then to simplify, we're going to combine things that are like on both sides, and then we're going to cancel things that appear on both sides. Right? So on my reactants side, I can combine these together, and I'm going to cancel out what appears on both sides, which is that intermediate, that N2H4. And so what I'm left with is my overall equation here. my nitrogen plus my 3 hydrogens give me 2 ammonias. Right, so it checks out. We got a legit mechanism here because these elementary steps sum up to my overall reaction. All right, and then I'm going to tell you about this mechanism here. We went in, we did the study. This is the slow step, and this second step is the fast step. So based on that information, give me the rate law of this reaction. All right, so when I do a rate law, I'm going to base it only on the slow step. This is my rate is equal to my rate constant K times the concentration of my reactants, rather. Okay, but I'm going to raise that hydrogen to the power of 2 because there's 2 of them involved in that elementary step. So then what is the overall order of this reaction? All right, this reaction is first order with respect to the nitrogen gas and second order with respect to the hydrogen. So the overall order is the sum of those exponents. So my overall order of my reaction here would be 3. Right? And this isn't something I could have figured out just by looking at that overall balanced chemical equation. But if I had that extra special piece of information we call our reaction mechanism here, then I can figure out my rate law. Okay? And we could sort of demonstrate this using those free energy diagrams. Okay? So I'm just going to kind of arbitrarily say that this is my reactant energy. Okay, so here's my product energy. Importantly, since we figured out that the delta G naught of this reaction is negative, that this is a spontaneous reaction, where should this level go? Up here or down here? Okay, this would represent a negative delta G. My delta G is the difference between these two levels here. So this is the thermodynamics of my reaction demonstrated. Delta G less than 0. All right, and we're talking about thermodynamics. That's the only thing I care about is those 2 endpoints. But if we're going to illustrate what's going on in the middle here, we got to look at our kinetics of our reaction. And this reaction occurs in 2 steps. One of them is a slow step. So it's going to have a really big activation energy barrier, followed by another fast step. So that's going to have a much smaller activation energy barrier. Right, this first gap here, this first little mountain that this reaction has to climb, is large, implying a slow step. The other one is just this little guy here. This activation energy is small, so this represents a fast step in our reaction. Cool. So again, the endpoints correspond to the thermodynamics of a reaction. Just illustrates whether or not this reaction is spontaneous or non-spontaneous. I guess I've got to be good. My y-axis for these diagrams here are free energy. My x-axis is reaction progress or reaction coordinates. All right, but yes, the green, the two endpoints corresponds to the thermodynamics of the reaction. And then everything that happens in the middle here, this corresponds to the kinetics. Right? Those activation energy barriers, that's what this reaction has to overcome to make its way from the reactant side. It's got to jump over this barrier here in order to get to the product side. Cool. All right. Obviously, in no way was that every single problem that we covered throughout the semester, but my goal was to kind of rewind back and pick little bits so that we can remind ourselves of what existed and what we learned this semester to give you a starting point for studying for your final exam, which you should definitely start now as opposed to the weekend before finals. All right, start breaking it into little bits that you're going to go back and review. Don't rely on one big crash sesh.
So during this problem, how did you know that the order was 1? Is that just something?
So the coefficient is 1, right? So the coefficient is what becomes the exponent. I wouldn't usually write it because anything raised to the power of 1 is just that thing. So normally you would just see it like this. But since I was calculating my overall order, I put that 1 there so we can see it more clearly.
Thank you.
Yep.
Also, is this going to be recorded, this lecture?
It was recorded, yeah.
Okay, cool.
Yep.
In the middle of class, I guess someone in Las Vegas hacked my card and ordered
Oh, no.
$70